Hello everyone, in our video we will talk about 1D continuous system. Firstly, we will present to you the 1D system equation, then we will talk about attractors, equilibrium and phase portrait. After that, we will give you summary where we will know what we have learned so far, and at the end we have the reference. So here we learn geometrical method of analysis of one-dimensional dynamical system. One-dimensional dynamical system have only one variable but can have more than one constants. In general, a dynamical system can be continuous or discrete, depending on whether they are described by differential or a difference equation. A difference equation is a discrete version of a differential equation. As you can see here, we have a fixed point which are not continuous. And differential equation is a continuous version of a difference equation. Here with this graph, you can see that it is a continuous line. One-dimensional dynamical system can be represented as V equal to f of V, which describes how the rate of change of B depends upon t. In this equation, V denotes the scalar time-dependent variable, which is representing the current state of the system. Here, V is the current state of the system and t is a time. In the context of neural dynamics, V is often the membrane potential and Fv is the steady state I to V curve taken with the minus sign. Now we will learn what does this graph mean and what are the components. Here we are given the graph which shows the trajectory of the dynamical system or a differential equation tends to follow. For our example, in this given graph, the phase space is given by x-axis. And in general, for a one-dynamical system given by dx by dt equal to fx, the phase space is the x-axis because it is impossible for a one-dimensional system like this, in our example, to move outside the x-axis. That is why, in this case, phase space in 1D is equal to x-axis. The path that any point follows towards the other point, for example, towards x1, in this case, this path is called trajectory. And here, x1 will be called the stationary point. So, a trajectory is basically a line or a curve which represents a path a dynamical system follows starting from some initial condition. This trajectory is always contained in phase space. Here, a trajectory is shown in a red line. As we can see that this red line is contained in the x-axis. This system behaves differently around 2 points xi. When I equal to 1, it is called a stable fixed point and it shows a negative slope, whereas x2 is associated with a positive slope and it is called an unstable fixed point. So stable fixed point, as shown by this red one, puts a system to an initial value that is close to its fixed point. The trajectory of a solution of the differential equation as x equal to fx will stay close to this fixed point, whereas unstable fixed points again starts the system with initial value close to its fixed point. If the fixed point is unstable, there exists a solution that starts at this initial value, but the trajectory of the solution will move away from the fixed value point. In other words, one can also think of a stable fixed point as an attractor and an unstable fixed point as the repeller. Now we can talk about the attractors. In any system, dissipation and a driving force tends to balance each other, setting the system into its default behavior. This typical set of state the system follows around its point of equilibrium is called an attractors. As we can see in this picture, given that state A and B are the state where all the nearby solutions are attracted. This is why these states are called attractors. In the field of dynamical system, an attractor is a set of a value or a state towards which assistance tends to evolve for a wide variety of starting conditions. Here, points onward this line are attracted to the state B, whereas the others are attracted towards A. Example of attractor is the use of addictive substances that are subject to the addiction body cycles in and out of the physiological influences, but continuously come back to the periodic and predictable fashion, that is until we are able to break free from. And this is what is so called the basin of attraction is. The stable equilibrium point is the only type of the attractor that can exist in one-dimensional continuous system defined in a straight line. R. Multidimensional system can have other attractions. Example, limit cycles. So the attraction domain of an state A is shown here, for example, this here. Whereas the attraction domain of the B is shown here. This is the attraction of domain of the A shown above with this line, and here the B. This is separated by the unstable equilibrium. This unstable equilibrium separates the two attraction domains. More about the equilibrium will be discussed on the upcoming slide. The state of the variable in 1D system changes depending on which side of the unstable equilibrium is the initial condition located. To analyze a dynamical system, we need to find its rest points in special states V, where Fv equal to 0. This is called an equilibrium condition. How the system behaves in a special state V is determined by the stability of an equilibrium, which is determined by the sign of the function around it. The sign of the slope Fv greater than 0 or Fv smaller than 0 determines the stability of an equilibrium. We calculate first the first derivative of Fb to calculate the slope. The equilibrium is stable when the first derivative, the slope, changes the sign from positive to negative as V increases, as shown in the first figure here. Obviously, all the solutions starting near such an equilibrium converges towards this point. And contrary to that, if the first derivative changes the sign from negative to positive as V increases, as in this picture, then it will be unstable equilibrium, and obviously all the solutions starting near such a solution will diverge. We can understand the concept of the unstable and stable equilibrium condition with the help of this illustration video. If you have a ball and a ball, let's pull the ball on the top of the ball, which is upside down. In this case, if we put the ball on the top of it, then the ball will roll down. This is because the unstable condition, which is the case of our graph x2. If we have a ball in a normal position like this, and the ball is inside it, then starting from any position, the ball gets rolled and will be stable at the bottom of the area after a certain time. So this is metaphorically the situation in x1 in the graph. So starting from any point, it will end up in the same point. This is called an attractor. Now let's talk about phase portrait. This graph is called a phase portrait. So the phase portrait is a geometrical representation of a dynamical systems. It depicts all the equilibria here, the stability, and the representative trajectories as well. It also depicts all the attraction domains. So what we have learned so far? We learned that 1D continuous system can have only one variable and one or more constraint. We also learned that what phase space is and what is phase portrait and what is a trajectory and a fixed point in 1D continuous system. Furthermore, we now can understand what is equilibrium state and their types as well. In short, we have learned all the components in the phase portraits. Thank you for watching. and here are the references.